Hello, everyone. Welcome and thanks for joining us for Building Embedded Software Efficiently with an IDE, part of our June-free webinar series. I'm Teresa Kisha and I'm your host today. With me today again is Maciej Halasz, Vice President of Technology here at TimeSys. And for those of you who are not familiar with Maciej, he heads up our EMEA office and he will be the instructor for today's session as well as next week's session. Today we continue the series with session 3, System Level Development and Debugging with TimeStorm. Once again, this event will be recorded and available following this session. And just to reiterate, you can use the exact same link you're using for this live session to view the post-event recording. Everyone who registered for today's session an email within the next 24 hours. In the email, you'll find a link again for today's recording, as well as a download link for today's presentation. With that, I believe we're ready to begin, so I'll go ahead and hand control over to Maciej to get things started. Thanks again for joining us, and we hope you enjoy today's session.
Thank you so much, Teresa. And welcome back, everyone. This is the third presentation in a series on how to use TimeStorm to develop embedded Linux-based systems. And today we are going to talk specifically about system-level development with TimeStorm IDE. Okay. Which APIs for development of a system-level software? So last week we've learned about how to approach development of applications. So the top red layer and part of the middleware if your application consists of executable and multiple libraries. Today, we're going to focus on the 2 layers below middleware, actually 1 layer below middleware, the Linux kernel. The Linux kernel represents an operating system in this case, operating system that provides an interface between our application software and the underlying hardware. It does it by providing a list of different device drivers, which each device driver is responsible for controlling the functions of a specific hardware component. And there are also device drivers that don't have any hardware associated with them, but allow you to interact with some of the Linux kernel subsystems. Okay? Nowadays, we also see customers design applications which implement parts of the value-add software inside the Linux kernel itself. And we also see applications where the device driver logic is being extracted from within Linux kernel and is implemented inside an application space, a user space. We always start with questions. So today, I have 4 questions. What are the typical tasks when developing a Linux operating system? We need to know the process because that process we either have to implement by hand to develop the Linux operating system, or we have to use some other tools that meet our criteria for development process. Do I need an IDE to develop Linux? That's one of the questions that we're going to tackle. Can I develop non-Linux OS system software in an IDE? And how do I debug a system-level software? So developing Linux operating system is one thing, but debugging it is a completely different set of tasks and requirements that we have to take a closer look at and find an appropriate way of debugging that Linux kernel. When we develop Linux operating system, we typically start by modifying the code. And I have this big red circle in here. Once we modify the Linux operating system core software, we can proceed to the next step where we have to configure some of that new code that we've added to a Linux kernel, or perhaps options that we've added for existing Linux kernel code to the Linux configuration. So we have to add those options through the configuration screen. And Linux kernel has the auto configuration built into the Linux kernel source tree. So you don't need any third-party tool to configure Linux kernel. The next step after we configure properly our Linux kernel is the compilation process. To compile the Linux kernel, we use the same cross tool chain as in case of application development. And the only difference compared to application level code development is that to compile the Linux kernel, we don't require any libraries. Linux kernel itself is self-contained, does not depend on other modules, library modules per se, and it's sufficient to have a bare bones compiler, a bare bones GCC to build a Linux kernel. It is also acceptable to build a Linux kernel with a different tool chain than the rest of the software stack in Linux. Right? So you can have a Linux kernel built with one tool chain, the file system, and your application with another tool chain. But we always advise that if you can build the entire software stack with the same tool chain, is always best, because then you don't have to deal with multiple tool chains for the same project, for the same system. Once we compile the Linux kernel itself, Linux kernel is going to produce one executable file, which is going to contain different device drivers that are built into the Linux kernel. However, some of the device drivers can be built as so-called loadable kernel modules. As loadable kernel modules, they are not merged into the single Linux kernel binary, but they are built as separate outside of that binary files, which can be loaded into Linux kernel as well. Those loadable kernel modules typically reside inside the root file system, side by side with the middleware. Linux kernel, of course, once it has the file system mounted, has access to those device drivers, and you as a user, through a script or manually, can load those device drivers as well. In many cases, development of device drivers consists of building a loadable kernel module first. It's on purpose like this so that you don't have to spend cycles necessarily on integrating that device driver that you're developing with the Linux kernel source tree proper, right? So for development, it's acceptable to build device drivers as loadable kernel modules and then decide whether this is how it's going to be configured for deployment. To develop a device driver, I have this smaller circle in here because once we set up a project for a loadable kernel module, it can live outside of the Linux kernel source tree. And as such, it has its own development process where I can modify the code and I can compile the code. So I can change the code and compile the code. There's no configuration for a single loadable kernel module. Okay. So those are the mechanics associated with building a Linux kernel and building a device driver initially as a loadable kernel module. One last thing that I want to mention before I move to the next slide is that once the loadable kernel module is inserted into the Linux kernel, running Linux kernel, it becomes an integral part of that Linux kernel. Okay? You cannot distinguish between a device driver and the other drivers that have been initially built into a Linux kernel. It's all one integral component sitting inside device's memory. Why would I choose an IDE for system-level development? I get that question sometimes, and typically the question comes from Linux kernel developers that have been developing Linux kernel for quite some time, And they have their own ways of developing the Linux kernel, their own preferred editors, and the preferred process of how they go about building a Linux kernel. So if you ask a question, can I build a Linux kernel entirely outside of an IDE without the need for an IDE? The answer is yes. You can use one of your editors of choice. You can compile the Linux kernel with a cross-tool chain that's provided by a software development kit. You can debug Linux kernel from a command line. But why would I use IDE? In many cases, the reason is that there's prior experience building operating system or an application with an operating system using an IDE. Most of RTOSes come with their own IDE. So if you're moving from an RTOS build environment and moving into a Linux build environment, an IDE is helpful. An IDE is a set of tools that will assist throughout the entire development process. The building and debugging of the operating system is quite complex. I would say that it's more complex than most of the applications in the embedded Linux that I've seen. Why? Because applications are modular. You simply build an application for certain requirements, but a single application does not provide the full operation, full software stack for entire platform, the hardware platform that you're working with. Linux kernel does. Linux kernel is responsible for all the devices that are sitting on your board. Linux kernel has to provide means to communicate with the outside world and means to communicate with the higher layers of the software stack, so middleware and your application. So there's a lot of code that's inside the Linux operating system. We talked about the fact that IDE, the letter I stands for integrated, and integrated means it saves time. There are those different aspects of development where you configure, where you compile, where you want to change the code and primarily debug that without an integrated solution, you're going to spend a significant amount of time setting up those different stages. When you start with an IDE, there's minimal Linux knowledge required. Also, what's important is if you have certain experience debugging Linux kernel on your machine and you want your colleague to have the same experience doing their own development, you can share your project, assuming that the colleague has an IDE, TimeStorm IDE, for example, and their experience should be very similar to the one that you see. Okay? So if you run into specific issues with a code and you want your colleagues to reproduce it this way by passing along the process, because you're passing the tools and the project, an Eclipse project, that helps reproduce that same scenario. Can IDE be used also to develop non-Linux code? The question always comes up, and a good example here can be a bootloader. In that initial picture that I showed you, there's a Linux kernel layer, and underneath was a bootloader layer. The most common bootloader today in Linux world is U-boot. And to answer your question, yes, an IDE can be used to also compile a bootloader. In many systems, however, to compile the bootloader, there's a preference to use a different compiler or a specific compiler. So sometimes you may need to instruct the IDE, hey, there's this other tool chain that I want to use for this project, but use these other SDKs for other types of projects and other compilations. To set up debugging for an IDE, or in general, to set up a system-level debugging in Linux, we have to first configure Linux kernel with additional options. And in this slide, you can see 1, 2, 3, 4, 5, 6 6 options. There's one dependency in here. And these options have to be selected when you configure Linux kernel. When you deploy your Linux kernel, these options are typically disabled. When you want to debug a Linux kernel, you should have these options enabled. Why? Because you can see from the slide there's something called KGDB. The slide is getting a little bit ahead of that KGDB story, but KGDB is a kernel GNU debugger, which is built into a Linux kernel. For application development, we were using GDB on the host, and then in the file system on the target, we have a GDB server, which is tasked primarily with starting the application and controlling the debug session on the target, and it also is responsible for sending information about debugged symbols back to the host side, where TimeStorm can assemble that information into several views and display all that information to you in a single IDE frame. KGDB is an equivalent of a GDB server, because when you start Linux kernel, there is no root file system. You can't start any other application. This equivalent of a GDB server must be built into a Linux kernel, and KGDB is it. It's a feature that has been available in the Linux kernel for many years now. There was actually a period of time where KGDB was abandoned, and without it, developers came to conclusion it's very difficult to sometimes just run a quick debugging session, because you have to resort to other ways of setting up a debug session. You would have to instrument the Linux kernel in certain ways, use some hardware-assisted methods, and those were not always available to everyone. So KGDB came back and became, in fact, one of the most popular ways of debugging Linux kernel. To boot the Linux kernel and to set it up for initial Linux kernel debug session, we have to also instruct the Linux kernel to stop at boot time. So assuming that you've configured Linux kernel with KGDB and all the symbols, it starts on the target in the bootloader itself, where you have something called boot args. You would specify these 2 additional options at the end of the command line. Okay, so we have KGDB OC. That means KGDB over serial, and we specify to which serial the Linux kernel should output or await the connection from a GDB. And then the GDB wait holds the Linux kernel once the initial KGDB setup completes. Okay, so this allows us to debug fairly early Linux kernel code. If you want to debug something that comes before the KGDB gets initialized, there's not much of a logic or much of code before KGDB gets initialized. But if you do, then you need hardware-assisted methods to do that. So we're talking about debugging with JTAGs. Okay, so once the Linux kernel boots with those Linux kernel arguments that we saw on the previous slide, the Linux kernel is going to stop at this line right here, KGDB waiting for connection from remote GDB. And at that point, you can set up a appropriate session in TimeStorm and an IDE and connect to the target. So that's exactly what we're going to experience firsthand today. Okay, so Linux kernel driver development. TimeStorm comes with dedicated project wizards to set up development of Linux kernel, and then separate wizard for loadable kernel modules, which, as we said, represents development of a device driver. Once the Linux kernel project is set up in TimeStorm, it offers to you ability to configure that Linux kernel from within IDE. You can then use the state-of-the-art editor to modify the Linux kernel sources. You can build not only the Linux kernel image, but in Linux kernel, the information on how to initialize the hardware nowadays is contained within device tree blob, which is a separate file that gets built outside as part of the build process, as part of the Linux kernel build process, but the DTB file is not merged into a Linux kernel binary. It is a separate, dedicated blob, a binary blob that typically gets loaded separately to device's memory by the bootloader. Okay, so these two images get built by TimeStorm. The third image that TimeStorm also builds, and that's all standard Linux kernel build process, is a file called vmlinux. By default, the build process of the Linux kernel will produce a compressed binary Linux kernel image compressed with a Z compression. So we would get something called Z image, which does not contain debug symbols. Why? Because otherwise it will be huge. It will be if we were to deploy the Linux kernel image with all the debug symbols to the target, we would consume a lot of memory. And remember, the memory consumed by the Linux kernel is the actual memory of the device. It's not virtual. So it's important to have a Linux kernel deployed on a device that does not contain debug symbols. So how do we know during the debug session where to go in the code? Well, there's this connection between the Z image and vmlinux, which is the symbol table. Symbol table is inside the Z image. And vmlinux, of course, has the similar symbol table available, so it can cross-reference whatever we want to access on the target and find the appropriate symbol on our host. So vmlinux is produced as part of a build process. You can also deploy Loadable Kernel Module, so run a device driver from within IDE. You don't have to leave the IDE, copy the module to the target, load the module by hand. No, all this is done through one mouse click by the IDE, by TimeStorm. And it's very easy to set up a debug session. So that's something we're going to experience today. Kernel debugging. So to debug a Linux kernel, we are going to use on our host a GDB that is part of the software development kit. It has to be a cross GDB. And we're going to have a vmlinux that contains the symbols that GDB can load into the local memory and access those different symbols while we debug. The connection, the standard connection offered for KGDB happens through serial port. Yes, it can be slow because we are talking about 115/200 baud rate for the most debug sessions, but it's acceptable, I think. I'll leave it up to you once you play with TimeStorm to come back to us and say, hey, this is not fast enough, or yeah, this is good enough. But the communication between the host and target happens to a serial. So target preparation for KGDB in TimeStorm or with TimeStorm is the same as if you were preparing the target for manual debugging. Okay. In TimeStorm, we're going to have a Linux kernel project set up, and it will be configured for KGDB with all the different options. TimeStorm will recognize the vmlinux by default. It will produce the Z image, and to debug TimeStorm, to debug Linux kernel with TimeStorm, we said that we're going to use the serial connection. So it happens that on that same serial connection, we typically have a console open. So it's important for us to close the console before we start a Linux kernel debug session, unless you have several consoles and you can set up your system such that the console is outputted on not the first, but second or third serial line, and debug always happens on the 0 line. Okay. So in TimeStorm, you're going to see that we have a dedicated actions in a context menu for these type of operations, for Linux kernel debugging, for Linux kernel configuration. There's a dedicated option. Okay, so rather than me showing you those pictures, what I'll do now is I'm going to switch to a live system, and I'm going to show you how the development and debugging is done. Okay. So we are in TimeStorm. You can see that I have some projects set up. Not to worry, I'm going to show you how this is done from the start. I of course had to pre-cook some of the projects because it takes some time to set up a Linux kernel project. So we have a Linux kernel project wizard, which allows us to specify a kernel name. So kernel session 3. And for factory SDKs, we allow you to select specific SDK, and all the lines are going to be pre-populated. For Yocto SDKs, because that information is not embedded in a software development kit, we will have to specify some of it by hand. So kernel source path, we would have to navigate, and yeah, this is probably okay. And you can see that kernel config was also picked up, because this source code was pre-configured, but you can, of course, specify a different configuration file for the Linux kernel. And then if you want to build a device tree blob as part of this project, you can simply check this checkbox and specify here IMX6 D Q nitrogen 6 max.dtb. How do I know the name of this device tree blob? It's one of the files that is embedded inside the Linux kernel source tree. So when I configure or build or configure Linux kernel for that specific device, I have to know pretty much where is my device tree blob, or what's the name of the device tree blob. Okay, so I'm not going to show you how this is done today in a session. We have separate training sessions about Linux kernel development and device drivers development. Here, we just enter the device tree blob name. Okay, so that allows us to proceed to the next step. I can create the project, so TimeStorm project data within the Linux kernel source directory, or I can simply copy the entire Linux kernel source tree from the location where I've identified where the sources live to my project. Okay, so if I do that, the wizard is going to well, transfer, copy, make a copy that I can mess around with. So before we finish the setup, we have to also specify some of the additional information here. So I want a compressed Z image and a load address. It's typically platform specific. So the default load address for the kernel is this for the platform that I have. And then in the next step, store output within project directory. Okay. And by selecting finish, the project is going to be set up. As I said, the copying is going to take significant time, so I'm not going to do that. Instead, I'm going to show you this project. So once it's set up, it's going to look like this. You can see that I have the entire Linux kernel project imported into TimeStorm. Now, using the context menu, I can access TimeStorm configure kernel. So I can navigate to menu config, and that's going to start a separate window in which I can configure Linux kernel, the device drivers, and so on. Okay? We said that we want to have the KGDB enabled. So I'm going to scroll down to kernel hacking, and you can see that kernel debugging is selected. If I keep on scrolling down, there will be a dedicated option for KGDB. Almost there. There it is. KGDB kernel debugger. So that option is already selected because I pre-cooked this kernel for our session today. Inside, you can see that it's configured to output or connect to our host through serial console. Okay? So that's exactly what I needed. This is how you can enable or disable device drivers, because I've navigated to debug features, but there's device drivers, and I can, of course, modify the composition of the Linux kernel built-in and loadable kernel module device drivers. Okay, so that's an easy way to change the configuration, which device drivers are going to be built. To build this Linux kernel, it's no different from a regular project. I simply say build project, and that's going to start the build process. Once the build is complete, I'm going to find the vmlinux at a top-level directory, and the binary Linux kernel is going to sit inside the ARM boot. Okay, so these are the images that I have to deploy on a target. So I've deployed those images onto the target. I've set up an SD card with the Z image from this build, and then I navigated through the source code to identify where I can place a breakpoint. Okay? So there are several breakpoints, and I'm going to switch to the debug perspective to enable these breakpoints right now. There's one in here. There's one in here. Okay. So, but typically, how do I place a breakpoint? I identify the device driver or where I want to place a breakpoint, and then I can simply click next to that particular line that places this line breakpoint. And if the code hits that line, the breakpoint is going to break into it. Okay. All right. So now, how do I debug? To debug, I select this, and I'm going to select TimeStorm kernel driver debug kernel. So that's going to start a TimeStorm kernel driver configurations view, where you can see I have an option already entered here for my Linux kernel. Okay, so that's the one. And what I have here is I have an executable image, which is vmlinux. Under debugger, I'm pointing to the appropriate GDB debugger. And that comes from this SDK, from this Yocto SDK. And then for the connection, I've specified, because this connection will depend on how I'm connecting to the target. My host is recognizing the serial connection as TTY USB 0. So this is the port on my host through which I'm going to connect to the console on the target. Okay, so we are ready to launch, but before we launch, we need to do one more thing. We need to reboot the system, and let me set up this USB 0. So this is my console. And I just press the reset button. So Linux kernel boots. It has in a bootloader those two additional kernel options specified, KGDB wait Actually, no, this one doesn't. So we're going to fix this. To fix this, on this particular board, I have to change the script. A script because the way U-boot works on Nitrogen 6X is that it reads a script rather than using environment variables. And after I booted, the first partition of the card is also mounted. I can show you that the first partition is mounted on the target's root file system right here. So I can access that. Run media MMC block 1. And here I have a dedicated script that has those two parameters set up. So I'm going to move 6x boot script to 6x boot script previous, and move 6x boot script kgdb to 6x boot script. Okay, let me sync to make sure that files have been committed. And now I'm going to reset the board again. So now it should boot with the kgdb OC set to the specific serial port, and it should use the kgdb wait. Okay, so you can see that I've stopped at the kgdb awaiting connection. All right, so to connect, I need to quit the console because I'm going to be connecting to the same serial port from the debugger here. And I'm going to say launch. So TimeStorm starts. And the setup of a serial can be a bit slow at first. And you can see that it's still in the setup. And I've hit the first breakpoint, MXC HDMI CEC. So somewhere in the HDMI initialization, I have this this breakpoint in here, right? So this is what caused the break in this code. So I can scroll down. You can see that there's a full stack. Let me expand this view. So I have a full stack here of how this particular driver was called. This is a driver that's built into a Linux kernel. And of course, you can see all the other threads in a system that are executing, and they have been suspended because of this breakpoint. OK, so now what can I do? I can use the same commands to step over a line of code, to go to the next line. I can also debug in the assembler. So here I am, going through this code again. And I'm out of this probe. And another, this code is executed several times. So let me resume, and let's see if another breakpoint is going to be caught. Yep, there's another one where I check for logical address. Okay. And again, for all that information, I have access to variables. Some of the variables may not be accessible in the kernel, but most of them are. So I can debug my Linux kernel code. And it's pretty quick, if you ask me, for serial communication. OK. So with that, I'm going to resume this. And once I resume, I can disconnect the debugger. So let's disconnect the debugger. Yep, I already detached. And now I'm going to show you a device driver. OK, connection is shut down. Good. So now I can go back in here. I can start a minicom again. You can see that my kernel booted all the way, okay, because I've resumed the debug session. So what I'm going to do right now is I'm going to switch again the boot files, move 6x kgdb, because for the device driver for loadable kernel module debug, I don't want to stop the Linux kernel awaiting the connection. So I want to just boot without a wait. That's why I'm moving these back. Okay. So now I can reboot the system. The system is going to boot all the way, and we can talk about device drivers. Okay, so for device drivers, TimeStorm comes with a dedicated C project. So I'm starting a wizard, and for a loadable kernel module, I have this hello world character device driver. So I can call this driver driver session 3. And I associate in the process the project with the same SDK as the Linux kernel. And what's more, I have to associate a loadable kernel module with existing Linux kernel project. That's important because the device driver cannot be built without accessing header files from the Linux kernel. Okay, so this is what it is. And so TimeStorm ties together all these options. And I'm getting a new project in here. I can build the project real quick. This is built, and you can see that I have a .ko file. I can open this main file in here and place some breakpoints. So I'm going to place a breakpoint in here. I will place a breakpoint maybe on module open. So these are the breakpoints that I'm interested in debugging. So now, using the context menu, I can access debug loadable kernel module, or I can first run the loadable kernel module. It's very easy. I set it up. I create an entry, debug loadable kernel module, device driver here. I can pass arguments. Debug configuration that I'm going to associate with is this Nitrogen 6X. So a debug session set up for Linux kernel is leveraged here. And to deploy a module to the target, I need also a TCP/IP connectivity. So we already talked about a hardware setup in the previous sessions. So at this point, I can simply say launch, and you can see in a console that the driver was successfully loaded. Okay, so that's how simple it is to see that the driver loads. Now, how do I debug? Well, the easiest is to navigate to Run, Debug Configurations. With that driver selected, everything is in place. We simply say Debug. And TimeStorm starts a debug session. So the debugger starts. Oh, I deployed the module before. Yeah, so when we debug, we should debug with a clean target. So this is what it is. So I've just reset the target so it doesn't have a deployed module in it. And we're going to quickly reset the debug session. So run, debug configuration. Target is booting. So I'll give it a few more seconds to come back. Okay, another 5 seconds. Okay, and I need one more of those pop-up windows that's going to tell me that the Linux kernel is fully booted and the network is really up. I need the network up because otherwise TimeStorm is not going to be able to transfer our executable through TCP/IP, the .ko file, to the target. Okay, well, let's give it a try. It will complain that it cannot connect to the target. If that's not, there it is. Okay, so let me check real quick what's happening. First of all, I had a console open, which is not an acceptable thing. You can see that debugging sometimes can have pitfalls like this. So this is still booting. Once it's booted, I'm going to leave the console. Okay, so we are up and running. Left the console. Now run. Debug configurations. And here's the device driver. Debug. Okay, setup takes some time to launch, especially the outer cache sync. I'm going to expand this so that we can watch this and watch this. And I made another mistake by clicking on the wrong device driver to test, I think. One last try. This is really the last thing that we're going to do in a session today, but I really want to show you how this debugging works. So the target is restarting. I'm stopping the current debug session. Okay. And let's debug this other device driver. Okay, so this is up and running. Oh, one more thing. There we go. Deploy module, then start debugger. So this option is used when you debug a device driver logic inside. If I want to debug the init code as well, I'm going to start a debugger, then deploy the module. That way, the function that is called when I initialize the driver is being called. So let's give it one more shot. Okay, so it's starting. Takes some time. You can see that it's still launching it. And now we have a driver loaded. Okay, so driver becomes part of the Linux kernel itself once it loads. And here we go. Okay, we are in a do init module. So there is the code that's being called from the Linux kernel when the init function is being called, and that's when it was broken into. And then I can step into the init code of the device driver itself and debug that functionality. Okay, so this is where I can resume my debugging. Do one init call, and it is already initialized. Okay. So this is how straightforward debugging of the loadable kernel module or device driver is. It really, if you're going to spend time with TimeStorm, you're going to have much better first-hand experience with what TimeStorm does, how it operates in those different scenarios. Whether you do application development or system-level development, the first-hand experience is always the best. So give TimeStorm a try. I hope that by now you already have a copy of TimeStorm installed on your host machines and you're already playing with it. Let us know what your experience is, or if you have any questions. We're here to answer your questions and help you in your development of embedded Linux-based products. So with that, I'm going to stop here. And let's take a look if there are any questions.
Thanks, Maciej. This was another great session with a lot of very good information on using our TimeStorm IDE for system-level development and debugging. We did have a question while you were presenting. And the question is, can other interfaces be used instead of serial for kernel debugging?
That's a very good question. The KGDB protocol used to have the KGDB over Ethernet. So there was once upon a time implementation of KGDB which would allow you to connect over TCP/IP. However, that code was not carried forward very much, and nowadays it's primarily over serial.
Great, great. And one question I want to, I did go ahead and I posted it in our chat panel, but just in case there are those out there who did not see it. Unfortunately, I apologize, we had a question last week after we ended our broadcast. I did not see it while we were still live. And the question was, the viewer asked about the availability of our TimeStorm IDE Windows 10 beta version. The Windows 10 beta version is available now, and you can find the setup manual for it on our LinuxLink website. Just simply log into your account at linuxlink.timesys.com and navigate to Tools, TimeStorm IDE. So it's the URL for that is linuxlink.timesys.com/IDE, and that'll get you to the setup manual. Any other questions? Please feel free to post them in the chat. I believe there's a little bit of a delay, about maybe a 10-15 second delay between our live broadcast and when our viewers actually see it. So we'll hold on for a few minutes just to make sure that we don't miss any questions this week. While we're waiting, I just want to go ahead and reiterate what I mentioned last week, that if you'd like to further explore TimeStorm, if you haven't used it yet, you're interested, you want to see more about dive deeper into some of these features that Mache talked about today. You can register for a free Linux Link account, which will allow you to generate a 30-day license for TimeStorm and unlock all of the features. It'll be the fully featured TimeStorm IDE that you can give it a try for 30 days. And in addition to that, you can also check out our playlist here on our YouTube channel. We have a TimeStorm IDE playlist. We currently, I believe, have 5 videos in that playlist. And we have a new video that we've recorded, which should be out on our YouTube channel by the end of our business day tomorrow. So be sure to check for that. Any other questions? Mache, is there anything else you'd like to add?
No, I think that we are also out of time for today's session. I could talk about TimeStorm for several days, actually, but given the time constraints, I'm going to stop.
Great. Well, I believe that's everything then. So on behalf of myself and Mache, thanks again for joining us today, and we'll see you next week for the 4th and final session in this series, Code Optimizations with TimeStorm. Until then, have a good day, everyone. Thanks for joining us.
Thank you.